Yellowstone National Park stretches over nearly 3,500 square miles of spectacular wilderness. Wyoming, Montana, and Idaho all claim shares in the dramatic vistas and charismatic wildlife.
The landscape that we see here is formed by numerous geologic processes spanning all the way back to 3 billion years old.
Greater Yellowstone sits on top of a volcanic hotspot where devastating geological events unfolded.
We had kind of 3 major caldera-forming eruptions, big explosive events, leading up to today.
Here we have kind of a series of volcanoclastic deposits, a bunch of different kind of individual volcanic rocks.
The prehistoric upheaval created a bizarre cemetery on Specimen Ridge and around Tom Minor Basin. These dead trees are made of stone.
The Gallatin Petrified Forest is a series of forests that were buried in volcanic debris flows.
We have these layers and layers of forest. Thanks to the volcanism, a big mudslide come in burying the forest. And then you have a new forest growing for maybe a few hundred to 1,000 years.
Greater Yellowstone's fossilized forests contain the remains of trees that died from molten lava, ash, and mud around 50 million years ago. The tremendous heat melted snow on the mountains, sending deadly mudslides rushing down the slopes, burying everything in their path.
So it will go down like a river channel, and anything that's in that channel will just be inundated with all that material.
Dr. Madison Myers is a volcanologist at Montana State University. Stumps, leaves, and even pollen were all preserved in the volcanic slides, resulting in a unique record of life during the Eocene.
This was the warmest time period since the dinosaurs died. We had no ice caps at the poles. In Wyoming, you had this very warm, temperate, to even tropical climate. It supported palm trees. It supported crocodiles, alligators, turtles, all these things that you just could not even imagine here today.
Dr. Ellen Carano from the University of Wyoming uses fossil plants to investigate ancient forest ecosystems.
One of the coolest things about plant fossils is that you can use them to interpret what climate was like. If you can just identify the fossil and you know what it is, if it's something that is around today or maybe something closely related is around today, we can look at where does that species live today.
The Gallatin Petrified Forest was just a normal forest, but you can imagine it being a forest at the flanks or at the base of a volcanic system. So for instance, thinking of Mount St. Helens and that eruption and all those trees that were then buried or knocked over by flows that were coming off of it during the eruption. Similarly, the Gallatin Petrified Forest was buried by repeated material coming off of these volcanoes.
It wasn't a one-time event. The area's volcanoes erupted continuously for millions of years. Yellowstone's Petrified Forest actually contains the remains of 27 separate forests, each stacked on top of the other, layer by layer.
It is so much bigger than almost any other petrified forest we know. 14, 15, 16, 17, 18, 19, 20. Okay, that's 20 years right there. So that kind of gives you an impression of how old this tree was. And it's bigger in a couple dimensions, most notably the up and down direction.
No other place in the world boasts a comparable record. One interesting feature of the petrified forests around Yellowstone is the strange absence of diagonal or leaning trees.
You could understand something about the intensity of that debris flow by looking at how much of it has been kind of knocked down. You would have to understand something about the strength of the trees.
Here at Yellowstone, you have that forest being buried in place. 20 plus times.
Despite detailed studies over the last 100 years, no animal fossils have been found.
Plant material is actually preserved more readily than animal material in these things. And I think part of that is because animals have the ability to move and run away if they hear that and feel that rumbling of something coming towards them, whereas you don't have the ability if you're a tree to move.
So it's actually pretty rare to find plants and animals in exactly the same layers.
Fossilized plant material gives us a more accurate snapshot of the prehistoric climate in this region.
I use leaves to interpret climate, and specifically leaves from flowering plants. So think of something like a magnolia versus something like an elm or a beech. If you go to the southern US, you see a lot of things like magnolias and dogwoods. Whereas if we're up in more northern climates, so you've got oaks and maples. So we have this modern relationship between the temperature in which a forest grows, and then we apply that same thing in the past.
Over 150 species of fossil plants from Yellowstone have now been described, but it's the big trees that draw the most attention. Some of the trees appear to be preserved in their original positions, while others may have been transported by mud or water.
But if you see a bunch of trees that don't seem to be knocked over within the flow, it's either that the impact of the flow wasn't high enough to knock them over, or that they were on a more level piece of ground. There is evidence that some of the petrified wood was transported. So for instance, in Tom Minor Basin, you can see like stumps of trees that are at all different angles and different sizes that seem to suggest that they may have been transported. However, there are other areas in the petrified forest that trees seem to be largely upright still and preserved in situ that way. So I think both processes likely were happening, that you had some that were transported in flows that were high enough energy or small enough trees, whereas others were just kind of covered by the material that were coming off of these volcanoes.
After each eruption and damage to the forest, the resilient trees began to grow again. But the forests were very different 50 million years ago. Yellowstone's petrified forest isn't the only fossil forest in the world, but it is unique because of how the trees were preserved.
The petrified forest here is different from the one that's located in Arizona, mostly by the process which formed the petrified wood. They both involve volcanic systems, but the way in which they were buried and which the solidification process occurred are different processes. So here, the petrified forest was formed through debris flows coming off of the Absaroka Range, burying the material in these kind of thick, really large, cobbly volcanic material. So some of them were standing, some of them were knocked down, and then solidification occurred.
In other ancient groves, minerals completely replaced every part of the trees over time. But in Yellowstone, the original organic matter and actual cells of the wood have been preserved within the minerals.
Yellowstone is this amazing volcanic system, and we have that to thank for the incredible preservation of these fossil forests. So we have this amazing source of silica all around. And then you have the hydrothermal activity. Superheated water is traveling through the rock, it's dissolving out some of the silica, and then that silica-rich, really hot water is permeating the wood. And so as it does that, it starts cooling and silica starts precipitating out in the empty pore space in the wood. And so in a lot of petrified wood, it's just straight up silica. But the way things worked here with the volcanism and with the hydrothermal activity, you have the silica precipitating out inside of the cells and a lot of that organic material then remaining in the cell wall, and it's been cut off from oxygen from bacteria that are going to decay it.
Most of the fossil trees in Yellowstone are redwoods.
Redwoods are some of the fastest growing trees on Earth. In good growing conditions, so lots of water, enough nutrients, good CO2, a redwood can grow something between 2 and even as much as 8 feet per year.
Today, redwoods don't grow in Greater Yellowstone. The region is now classified as subalpine. But Ellen can tell from fossil leaves that Yellowstone once enjoyed a subtropical climate.
A well-preserved leaf looks like it just fell off of the tree, and you can see every single detail, the outline of the leaf, the veins, every tiny little bit of venation on that leaf. And you know, they're just gorgeous. 50 million years ago, here in the Greater Yellowstone area, the mean annual temperature would have been something like 70 degrees Fahrenheit.
The area probably received 50 to 60 inches of rain each year. Like any forest, living or fossilized, insects play a key role in the health of the trees and plants.
That's a big one. Let's say that an insect chews a hole in a leaf. The leaf can't repair itself. It's not going to grow new tissue to fill in that hole. But what it's going to do is it's going to make a thickened rim of tissue around where that damage occurred. So looking at damage can tell us something about insect diversity. And this is something that can be really interesting during times of changing climates. As CO2 levels increase, plants actually become less nutritious.
Average temperatures in the park are higher now than they were 50 years ago, especially during springtime. And nighttime temperatures are increasing more rapidly than daytime temperatures. We may be headed back to the Eocene.
Peak warming was between about 53 and 51 million years ago. And fun fact, if we continue burning fossil fuels by the year 2140, Earth's climate will be a lot more similar to that peak warming than it is to today's climate.
The investigation into Yellowstone's mysterious petrified forests will continue for a long time. The scientists hope to use their discoveries to help to predict what the rapidly changing climate might mean for Yellowstone in the future.
The fossil record gives us this opportunity to see how ecosystems are changing in response to climate change, both the temperature and the carbon dioxide levels.
We always are studying past climate to try to understand something about future climate, for sure.
Yellowstone's fossil forests provide geologists with a window to the past that may be a critical window into our future.